Hello and welcome back to Calculus 3, section 11.3 dot product. So this lecture and the next one, 11.4 cross product, we'll talk about the multiplication of vectors, right? Excited? Good. So the first one, the dot product, is a multi-dimensional extension of the product you already know. What's 3 times 5? 15. Very good. 3 times 5 is 15. What's 3 times negative 5? Negative 15. So let's just take that knowledge and make it multidimensional now. That's all we're going to do. You can do dot product in any dimension. So dot product can be done in any dimension. Now, Calculus 3 is only concerned with two-dimensional things and mainly three-dimensional things, which we are going to, we're going to limit ourselves to those. When you take linear algebra, or if you already took linear algebra, you know that you can do this in 18-dimensional space if you want to. Now, in one-dimensional space, I just echoed myself. In one-dimensional space, the dot product is just your regular multiplication. And as I already asked, what's 3 times 5? You all said 15, right? And 3 times negative 5, negative 15. So if you want to think about it, you have the one-dimensional multiplication, the dot product. One-dimensional dot product is just the basic multiplication you know. And now we're going to go higher, and we are going to take a look at the 2D and the 3D dot products. So we start first with trying to figure out what this actually means to have a dot product. It's not too clear, and even if you read the book, I think it's not too clear of what is going on. And the part of that is because the concept is a little bit abstract. In a nutshell, I would say that the dot product would like to isolate things that are the same and multiply them and just get that I want to say mass, right? That everything that exists and it's moving in the same direction. If you look at the definition for the dot product and the way it's defined and the way it works, and I'll do that here in blood. So here's the definition for it. If you have a vector u dotted with a vector v, right? The dot product is going to be the vector u x component and the u of y component dotted with the vector v x component, comma. So this is me just rewriting the same dot product. And here is the formula. It's u dot v is equal to ux vx, that's a multiplication, plus uy vy. So this is the dot product in 2D. So I'll just put here a 2D version. It's not the version, it's 2D version. Oh well. And as you can see, you are multiplying x component with the x component and y component with the y component. And then you are adding all of that together. The answer is always a number. You know that 3 times 5 is 15, which is a number. So multiplying two vectors through the dot product returns a scalar. And a scalar, meaning just a number, And that scalar you can understand in terms of how much common things are there for these two, the vectors in terms of respective dimensions. So how much you would go in x direction and how much you would go in the y direction, and you just add all of that up on the pile. Now, there is also the graphical representation of this in terms of projections to understand. And then if you take linear algebra and look into very deeply into this concept, you can also find more arguments for why this is valid and the way it works. So from standpoint of this class, this is Calc3. You just need to know how to use this and what it's used for without actually going into the linear algebra aspects of this to understand the graphical ramifications when you have two vectors and how their projections work to do this. Some of the counterintuitive ideas of why would this be commutative at all, especially when you draw this thing and you see that the projection of u to v is not the same as v to u, which is which plays a role into all of this. So we'll take a look at that. I just want to grab some examples real quick. So the 3D version of the formula u dot v is going to be ux vx plus uy vy plus uz vz, and that will be a 3D version. Now there are other formulas which also are used to get this. Now you can extend this, as I mentioned earlier, you can extend this to any dimension. So if you need the 18-dimensional, for whatever reason, dot product, you can do this. So let's just get the mechanics out of the way, and then we can actually start using it in the calculus setting. So what is the vector 3, 4 dotted with the vector -2 and 8? So you would follow the formula, plug everything in where it belongs. If you did class prep, you had to understand this much at least. What am I multiplying? Yes.
3 times 82.
Good.
And then it's going to be minus 8 times 4.
Y minus. Plus. 4 times 8.
So now it's going to be plus 8 to 4.
So I have -6 plus,
32.
which answer is? Very good. All right.
That's why I'm writing it.
What happened?
I'm just writing everything down.
No, you're right. 26. That was correct. I got you. All right, let's do the 3D case. So, how about the vector 3, -1, 2 dotted with the vector 1, 2, 3. Very creative. There we go. So 3 times 1 is 3, minus 2, plus 6, 7. Good. So we know how to compute the basic dot product. And now let's go a little bit deeper into the concepts here. So there is another definition for the dot product, which is a definition that involves the dot product, the magnitude of each of the vector, and the angle between those two vectors. And that formula will further explain this idea of the idea that the dot product measures how much of the same vectors have amongst each other. So if you look at this particular definition for the dot product u dot v, which are vectors, is the magnitude of u times the magnitude of v, this is the regular multiplication, times the cosine of theta, which is the angle between two vectors. I am not going to draw a coordinate system for this, because if I put coordinate system x and a y, you are going to marry this idea to x and a y. This is actually anywhere in space. So I'm just going to draw two vectors like this, vector u, vector v, and the angle theta between them. We know how to find magnitudes. We know how to find cosine of whatever angle we have. So we should be able to compute dot product this way as well. Now you need to know both formulas, because certain problems will call for one type of formula and certain would call for another. Further on, going through for those of you who want to join the honors option in this class, again, the proof will call for one form or the other. Depends on the situation. So now, the interesting part over here is to note this angle, right? The cosine theta. So there is angle between two vectors. And that is something very useful to think about. You guys have multiple notions out there, multiple applications for the dot product, and one of them will be work. And we are going to talk about that in this lecture, the work in physics. So most of the time, when you have something that you want to push, right, if it's not as tall as you are, like let's say this crate, sits on the floor, generally, because you are taller than a crate, you would lean against the edge and you would push. But if you observe the vector F, which is the force with which you are pushing, that vector can be decomposed into the component that it's pushing down, which is waste, right? You don't get to bury this crate into the ground. So all of that is wasted. And then you have this one. You see, as much as you push down onto the crate, the surface on which the crate is will push up. And you just end up losing all of your energy and all of your strength, your calories that you worked so hard for. These guys over here at the beginning of the class. So we're going to discuss these things in detail, right? But you can see also the angle theta, right? The angle of attack there. And we're going to discuss the work, and we're going to discuss the importance of this angle. So by simply rearranging the formula and using the inverse cosine, we have that theta is equal to inverse cosine of u dot v, which we know is the scalar component, right? We did two examples over here. We got 26 and 7, right? So we know that's going to be that. And then you also have the multiplication of the two magnitudes. Each magnitude is a scalar value as well. So you're going to have a cosine of a number. Now that number better be in a range of -1 to 1, or you broke mathematics. So this formula, again, is just a flip of the formula up there, will give you the angle between two vectors. And again, extremely important in our application. So find the angle between vectors u equals 2, -1, and v equals 1 and 6, whatever. Now you will have to use your calculators, and for this particular, this is something that will be heavily used in engineering. It is okay to give your answer in degrees, but then make sure your calculators are going to give you the degrees back, and then make sure you switch the calculator back to radians to graph. All kinds of hell break loose when you start playing with that mode button. So you have to be very careful about that. Your cell phones can also find the cosines. Lou, don't bother her. She's trying to do work.
Did you?
Oh, they're checking the answer.
I got 107.
You actually did. Did you get 107 degrees for that?
He got,
That's what I got too.
You got 107?
Yeah.
I was asking for static.
apparently 107. You loving it so far? It's good. You better love these courses because it's your life. This is it. This is what you signed up for. Is this for the end of your life? All right. So first I will need both of the magnitudes, which is in this case, square root of 5 on the first one. And the magnitude on the second one is square root of 1 plus 36, which is square root of 37. So theta is the inverse cosine of the dot product. So the dot product is 2 minus 6 divided by square root of 5 times square root of 37. So cosine inverse of negative 4 divided by, we can get the decimal for this one, hopefully. $13.6 0.14, but 13.6. And now we're taking the inverse cosine of this. So inverse cosine of negative 4 divided by 13.6. And we get 107.1 degrees. So the angle between these two vectors is so. Now, definition of orthogonal vectors is if the dot product is 0, two vectors are orthogonal. Now, you are used to the word perpendicular, but that word applies only for the 2D case. It's a word that it's reserved for 2D case when you say that there is 90-degree angle between two lines. For the higher dimensions than 2, the word is orthogonal. So word orthogonal means that two vectors are 90 degrees, right, to each other, 90 degrees in 3D, 4D, 5D. So you can actually also use orthogonal for 2D instead of perpendicular. You can actually take the word perpendicular and completely take it out of your vocabulary if you want to. You'll be fine. But it's not proper to use the word perpendicular in 5D space. The word is orthogonal. So now we have a way to see what the angle is between two vectors. And if that angle is 90 degrees, we are going to claim that the vector, that's by definition, right, the vectors are orthogonal. So that's also given as the definition. So two vectors are orthogonal if and only if u dot v is equal to 0. Two vectors are orthogonal if and only if u dot v is equal to 0. The statement if and only if can be shortened by the IFF, right? So IFF is the if and only if, and the wording implies both ways. You can start with the notion that you have the dot product is equal to 0, in which case you will get the two vectors to be orthogonal, or you have two orthogonal vectors, that means that the dot product will be 0. So not everything in mathematics works backwards like that, right? Some of the theorems work only one way. So the if and only if is the wording that asserts that you can look at this one in any way. Yes, Luke?
So wait, orthogonal has to be 90 degrees?
That's what it means.
So it's 90 degrees, so orthogonal.
Yes. So you can have a plane like a wall, or see, I am orthogonal to the floor because no matter which way you measure the angle, right now as I'm standing upright, right, it's going to be 90 degrees. Now, in this case, I'm no longer orthogonal to the floor because there is an angle. You can also take the plane and set something to the plane. So if there is 90 degrees, now there is a vector in this plane to which this is 90 degrees. So if I pick a vector and I do the dot product, it will be 90 degrees. So that's what the word orthogonal means. There is a 90 degrees between the two vectors. Now, one of those two vectors could be in the plane, and then you can say that the vector and the plane are 90 degrees. Good. And we will come back to this. We are going to use this as we move along. And so now we have some properties of these dot products. So properties of dot product. Number one, dot product is commutative. So u dot v is the same as v dot u. And again, those of you in the honors, the ones that are signing up for honors, this would be one of the proofs that you will do. You can assume the commutative property in 1D, and clearly that will help as you write out the proof, because you actually do have, in the definition, 1D multiplications where you can swap things around. So, so that's that, right? So the first property is commutative property. The next one is the associative property, where C dot U dot V is that you can multiply C dot U dot V, or you can go U dot CV. So that will be associative property. And then finally, distributive property of the dot product. So U, vector U, dotted with the addition of two vectors is going to be distributive. So you can distribute these vectors and get it. So you should be able to do all of these proofs. And you can use, just to make it short on writing, you can use 2D vectors, it's fine. So you will have either ux, uy, or you will have u1, u2 as components. Those of you that are really ambitious, go ahead and do it on the nth dimensional space. So your vector u will have components u1, u2, u3, dot, 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 un. V will have the same thing, 1, 2, 3, dot, 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 n as components, and you can just manipulate. But, to learn these kind of things and to start off, you just, you always do the 2D case just to see, and then you just extend that to whatever amount of dimensions by adding more components. So those would be additional. So you have those 10 properties that we talked about on the other day, and then now you have these 3 properties of dot products that are added to the mix. And finally, we get to the point where we talk about orthogonal projections, which is the heart and soul of these. So, orthogonal projections. I think I've seen this for the first time in the pre-calculus course, actually, when I took the curriculum many moons ago. Whenever you learn trig, right, you start talking about angles, and then eventually one of the greatest applications, right, for trig would be vectors, and then there has to be some kind of angle between vectors and then projection. And it took me some time to get this projection business, because it is not intuitive until you really, dig into it. So let's take a look at orthogonal projections. Plural, right? Projections, not one, but you can have two or more. First of all, the word projection, guys, that's at its base core meaning of the word. The device over there is called a projector, right? And it projects the image onto the surface. So if I interfere, right, projecting now on my hand instead of on the surface, and you can see the shadow where I hide. Eclipse, it's another thing. When the moon gets in between the earth and the sun, right? So the sun would be the one projecting the light, right? And then the moon would get in the way, and we would have the eclipse. Projection literally means what it means in this sense. You can think of it as shining light, and we're going to worry about the orthogonal projection, which means we're going to worry about the light rays that are coming in perpendicular to the surface. Now, linear algebra can skew all of this, and linear algebra will allow you to work in any framework. What we are doing right now is not going to be enough for you to construct a projector, because the projector is not standing, right? You would have to use this. You would have to have the projector that is this side standing in front, projecting exactly 1 to 190 degrees to each pixel, right? Clearly, that's an angle, right, and all of that. So linear algebra has its immense use for in the design, things like this. Now, what we want to know is now, and this is literally a baby step in comparison to what you need to know to get that thing working, is you want to know that you have a base vector that sits on the floor, right? And think of that vector as a floor. And then you have another vector that you are projecting onto it. So now, as you shine the light, let's use the purple light, right? So as you shine the light, and this light is 90 degrees to the surface, to the floor. I should have drawn this angled. Yeah, the first picture, I'm going to actually make it straight, so it's easier to understand. So here we have Mother Earth. It's flat, all right? Thank you for laughing. No, I'm serious, thank you. Over the summer, I was behind someone. I took a picture with a bumper sticker, Earth is flat. Or Earth is really flat, or whatever. I can look back. And then I just drove by. I went out of my way to actually just go side by side and look inside. And his face actually matched the sticker, so yeah. Anyway. So sometimes you can just tell.
See you tomorrow.
See ya. Wait, we have no class tomorrow, next week. So what I'm going to do is I'm going to unleash this light, which is going to be perpendicular to the surface of the Earth. And as you can see, all of these guys here are going to be hitting the vector, creating this shadow on the Earth, and the ones past that point will be still illuminating the surface. So what I have here is, we call this vector u and we call this one vector v, right? The red vector is called projection of vector u onto vector v. Now I want you to stare at this notation, and notation-wise think logs. Logs have the same notation. You have some letters, and they have a small number on the bottom and a large number, right? Where the small number was base, and this was the answer if you do the inverse for the exponential functions, right? So thinking about that, you are projecting u onto v, and v is the base, so v is the floor, right? And the vector v is the one that you are projecting, and the answer is the shadow. The answer is the shadow. So if I do this, what I want is the shadow, and I don't care about anything else that's illuminated. All right? And technically, this is what the projection of my hand is on this thing, given that that's 90 degrees, right? The orthogonal projection. Lou, what is the...
Now you answered. I just wasn't sure when I was looking at the homework. I was trying to say that the projection of u over v, right?
Yes. Which is the reason why I mentioned logs, because if you guys are reasonably good with logs, and you should be, because, I mean, you really don't want to be, you know, discriminating against operation, right? Mathematical operation. So when you look at the log, base 2 of 5, right? Log base 2 of 5, this one is your base. Well, technically, this is your base as well, but we don't call it a base. We say onto v. Well, yeah, that provides a base on which you are going to see that shadow that you were after. So, orthogonal projection is very simple to understand, and I encourage you to actually take a pencil and a flashlight and then just, you know, click and see. Now, I mean, I believe in doing these experiments because you actually get to see this thing alive. So what you can do is you take the pencil, you put it at some angle, 45 degrees or whatever, you shine the light from above and observe the shadow, which would be, you know, some length. And then holding the lamp steady, change the angle, and you will see the shadow get longer or get shorter. It's the same pencil, right? The same length pencil. But it depends on that angle, and you will see quickly that the projection, the length of the shadow, depends directly on the angle at which you angled your pencil, right? Your light source is not moving. The vector is not moving apart from changing the angle. The size of the magnitude of the vector u doesn't change as well, right? So it's just this angle at which you have vector u. So now you see that the dot product will play a key role. There should be common sense from this image. The dot product is playing the key role for you to construct the formula to find the projection, which is the shadow piece. Again, you go and get your imagination run wild. What are the applications that you can, you know, fit this in? And there are thousands. I already told you I want to construct a projector, but then also I talked about the crate, and we're going to revisit that very quickly. Matt.
So the u vector has to be off the v vector. You know what I'm saying? Like, say, for instance, you can't have it parallel above it. You know, I mean, maybe I'm just thinking a little
No. That's a valid. So first thing that you said, the two vectors are parallel. Well, if two vectors are parallel and we have the notion that vectors are free to move in space, you will actually superimpose U onto V. So actually they will be overlapping, they will be on a pile.
Yeah.
And then as you shine the light, you will see that U is actually just itself, it's U.
Yeah.
Because it's its entire length and it's parallel. And if you stretch it all the way up to be 90 degrees and you shine the light, it will be 0, right? And you clearly see that, oh, 90 degrees up, orthogonal, 0, U dot V, 0. All of these things play a role, and as I write the formula, it will immediately be clear. So what I'm going to do here is I'm just going to point over here and say light, and I'm going to point here and say shadow. So as you do this, it'll be clear. Oh, by the way, this is also another way for you to prove when you run into someone who tells you that the Earth is flat. So, at noon, at one point on the planet, when the sunlight is 90 degrees, you are going to have no shadow when you put the stick in the ground. And at that same instant, somewhere else in the world, you are going to see a shadow. And the only way, right? Look into it. So there you go. That's, you don't have to go with a ship in a sea and you first see the little bit of a ship and then the whole ship, right? There you go, right there. So projection and a shadow. Good. So now we have this framework, and let's write the formula and then look into the formula and see. Now there is in the book, there is derivation for the formula. Those of you who are in the honors part, again, you are responsible to derive this formula. So your question on the exam might be just derive the formula for the orthogonal projection. The non-honors part, the problem will say compute the projection and then two vectors are given. So that's the difference in the problems. They have this going on for one page in terms of the length, and it gives you the entire thing. So the formula that you guys want, we are going to discuss this in detail now. So projection of vector u onto vector v is going to be the dot product of u and v divided by the square of the dot product of v with itself times vector v. Hoo-hoo. Formula to calculate projection of vector u onto vector v. I'm going to underline the word onto. All right. No comment. Oh, it's sleeve. Oh, that's... So now, what I'm going to first note here is that, I mean, you don't have to know all the subtleties of this, but it's helpful if you do, and I don't know, probably help you remember the formula too, or you can just write it 50 times. So hopefully we all understand the concept, and if you don't, you go home and you try it with the light. Maybe you can, if you sit under one of these, you can play with the pencil a little bit on your desk. the angle for vector u determines the length of the projection. Now, your projection is a vector. The red arrow, the shadow, what I call the shadow, the red arrow there is a vector. It has to have magnitude and has to have direction. So it goes without a say that the direction of the red arrow is the same as the direction of the v, because that's where it lives, right? And that's this times v at the end. So you have the two dot products and then you have times vector v. So that vector v is going to give you the direction. Now the issue with that is clearly vector v has its own magnitude that has nothing to do with vector u. So what I have to do is I have to scale that one to its length 1, because I need the direction of v and the magnitude of whatever u and the angle give me. Longer u, longer red arrow, longer projection. As you decrease the angle towards vector v, projection is longer. As you increase the angle towards 90 degrees, it's shorter. So all of these things play the role at the same time. Now look, what I can do is I can say v, vector v, or 1 at the end, divided by one of these puppies in the denominator, right? Its magnitude. What I'm getting there is I'm getting the unit vector. Now unit vector has the length of 1, and whatever you multiply it by, it's going to be that number. So unit vector has a length of 1, and then the direction of the original vector. So technically, if you are to write this v dot v in terms of the magnitudes, right? This is a dot product, so you can write it as the right cosine. You see that these are actually two magnitudes. So this divided by the one of those guys is going to give you the unit vector. And then the dot product up there has the cosine, right? And that cosine of the theta is going to impact the length of the projection. So technically one of these guys is going to give you, with this guy, is going to give you the direction, and the other three are giving you the length of the red. And all together you get this. Now, it looks convoluted, but it needs to be that way because v doesn't have to be x-axis. V doesn't have to be the flat surface onto which you're projecting. It could be any other way, which is what I actually wanted to do at first, but I decided not to. So if I have my vector v to be here and the vector u, well, now I have to draw the light perpendicular to v. So it's not going to come from straight above, it's going to come at an angle. And that angle has to be the same angle that v makes with the x-axis, plus 90, right? So the incoming light is now going to go like this. And your shadow is going to be here. And this is still the same projection of vector u onto vector v. Now we just turned the entire system, which is okay, right? Another beauty of linear algebra is you learn linear transformations. And in that course, you learn the way to rotate this and then bring it back to this picture. And they're equivalent, because they are. You just need to multiply it by the rotational factor, which is a matrix of trick stuff, sines and cosines. So you can rotate coordinate systems. That's also very useful in physics if you have the object on an incline like this, right? And then you consider all the forces, the force down the incline, the friction going up, the normal force always perpendicular to the surface, and then the weight always pointing downward. If you look at this, I have 3 forces on an angle of whatever theta for the incline is, and 1 force that it's straight y component. Some of you are taking statics right now. Oh, that class would be much easier if you understood linear algebra like that. Because look what we can do. I can just take this inclined plane and make it straight. And then just the block sits on it. And so now normal force is going this way. Force down the incline goes this way. The friction goes that way. And the only thing that is skewed is the weight force. Just by simple rotation. So now you're just adding x to x components and y to y. You just have to do 1 trig decomposition instead of doing 3 trig decompositions. And this is why I say that mathematics is for lazy people, right? Because while all the other peasants are decomposing 15 vectors, I get to decompose 1, right? So you go figure that out. So now the same thing is going to be here for projection, and then you see that this formula up there doesn't care whether you are, in what frame of reference you're talking. Is it going to be the flat or vector v is not going to hit the x-axis. It's just whatever the direction of vector v is, that is going to be preserved in this vector v here. And that one gives you the direction, scaled by one of the magnitudes from the bottom to give you the unit vector, so its magnitude doesn't matter. And then the rest of these guys are going to give you the length of the red, which is the magnitude. So when you put them all together, you have the magnitude and the length of the projection. So you can either, learn and reason with it, or you can just memorize the formula and be done with it. Now, we are going to actually consider, we're not going to use this many forces. We could for the block. But let's first just calculate, the vanilla problem, where you calculate projection of... oh, by the way, can I project vector v onto you? What do you think? I can. Flashlight is free to move in space, right? If I have 2 vectors that are set in space, and I can make 1 vector long, it doesn't really matter, right? So I have 2 vectors in space, like this, and this is the system that I can't move. I can shine the light 90 degrees to the blue, or 90 degrees to the green. So I can calculate the projection. Now, you are used to seeing in pictures and maybe in other courses the projection on green onto blue, because green is shorter, right? So you can actually find a nice little red vector here. But guys, the length of blue doesn't matter. You can extend it any way you want. Remember that this is the vector you are projecting onto, and that one is scaled down to the unit vector just because you need the direction of it. You don't need its magnitude. So it's okay to project blue onto green, because you can extend this infinitely far. You are talking about the unit vector for green if you're projecting this way, just to get its direction. Yeah, sure, this is going to project somewhere up to here, but this line has its direction forever. And that's the part that you need to understand. So this stuff is not commutative. So projection of u onto v is not the same as projection v onto u, but you have to be very careful which projection you need in order to do the problems right. So I'm going to ask for both now, and I want to see your ability to massage the formula and change it to get the other projection, because you can't use the same formula for the other projection, right? You need to modify the formula that I say using common sense. So given let's do 2D vectors, so we are not here till tomorrow. 3, -1, and so u, vector u, is 3, -1, and vector v, 4 and 2. Find part A, projection of vector u onto vector v, and part B, projection of vector v onto vector u. So again, the second one requires of you to massage the formula and figure out what you have to replace in which way in order for it to work.
You better have an answer to be a vector which encodes both things. Right? So you have a scalar times a vector. That's going to be a vector. The answer has to be a vector.
Welcome.
So wait, so for here, let's say we should do you want to like 12. 12 plus 2 times 8. And on the bottom, it's going to be just this. So now it's like I would say 1 over 1. 4 now, right? So now we times this by this. I don't know. Did you get this? You get 20? I don't know. Is this right? 40 over 20? Wait, what is that? Comma? That could want me to stop. Okay, so this goes to half. Yeah. 4 over 2 times half. So now I get 4. Now, you gotta multiply.
What's your final answer? Is
4 times 1 half. So it goes into 2. 2 times 2. So the 2 comma 1.
so
Yeah, now we have
That's my name.
now we have
this times itself,
No, that shows that's
and then multiply by that,
which here,
just multiply by a scalar. So
that's your vector. They fix it.
yeah, because like look at this is definitely a vector, so it's only fine to just write it as well.
Remember, I'll be going around asking you to tell me other people's names. So maybe on Wednesday, maybe next week. That includes people to the sides, in front, and behind, because you're supposed to check answers and things.
Alright, so I got 2 comma 1.
Yeah, I don't know. I haven't done it yet.
I know, but do I have to do something? Well, let's look at the homework. I'm forgetting things now. Don't I have to do something with cosine inverse theta? Why am I I'm overthinking. What do you do best? Yeah, 2-1. I didn't do this second one
You got 7? Did you get 7? Yeah. Okay, good, because that would be wrong. Okay, so we're going to need a whole bunch of these magnitudes. So before I start working on either A or B, did anyone get B so far, the answer?
Yeah.
What do you have for B? I just want to write it down.
3 -1.
Yeah, 3 -1.
3 -1 for B.
Yeah.
And what's the answer for this one?
2 1.
2, 1.
2 1.
Yep.
2 1?
Yeah.
Really?
Yeah.
Yeah.
Why?
All right, I'm happy. I don't know why. Just sometimes I'm just happy like this. It passes. It passes. Don't worry about it. I won't.
You think it was gonna be over?
It's just gonna go away. Yes.
No, it's just gonna go away. Wait, the happiness or the answer?
The happiness.
Oh, okay. Okay, I was gonna say, oh. Okay.
So we have 9 plus 1 is root 10, and magnitude of V is, oops, 16 plus 4, which is square root of 20. Now you'll see why I want this later. Now, okay, let's go to the projection. So part A, projection of a vector U onto vector V is the dot product U dot V, V dot V times V. Now all these are vectors. The dot product of U dot V, that's going to be 12 minus 2 divided by V by itself is 16 plus 4. So that's 10 over 20, that's 1/2. Oh, times vector V, holy nightmare. So 4, 2. So now this projection of vector U onto vector V is 1/2 times 4 comma 2. That's now scalar multiplication, so 2 1. Yay. Now part B is the projection of vector U, of vector V onto vector U. Now the formula is still U dot V here, but now it's U's everywhere. Because U is the base onto which you are projecting everything else. And we still have the same dot product, which is 12 minus 2. But now we have the vector U, which is 3 and 1, so that's 9 plus 1 is 10. Times vector U, was it negative 3, 1 or 3, negative 1? Negative 1, all right, thank you. So now I have 10 over 10, which is 1, times 3, negative 1, and we have 3, negative 1. And there they are. So this is projection of vector V onto vector U. Good. Now why do I want those magnitudes up there? I just wanted to check that the vector V and projection in A have the same angle, which means direction. Sorry, they have the same direction, so I have to calculate the angle. And then I also want to check for B that vector U and this projection have the same. Now that part is easy because we ended up with the same vector, right? So that definitely matches. But I also want to see that my vector, oh, well, this one, it's only a half, right? So it's easy to see, but you can calculate. So vector v is 4, 2, and the projection of vector u onto vector v was 2, 1. So you can find the cosine. This is a check. So you can find the inverse cosine of, let's call this v dot projection of u v, right? U onto v. That's a vector. Divided by the magnitude of v times the magnitude of the projection. So inverse cosine over here, when I do this, I get 8 plus 2 divided by the magnitude of v. Where's the magnitude of v? Root 20 times the magnitude of this one is 5. Cosine inverse of 10 over square root of 100, which is also 10, cosine inverse of 1, which is exactly 0 degrees. So two vectors have the same direction if the angle between them is 0 degrees. It's very simple, right? So this was a confirmation for us that we have this problem right. The last concept is the applied concept of calculating work. So it's now physics. Some of you might push to dynamics later on and so on. So this is a good concept which states that the work is equal to the force times the distance covered. It's a dot product between them. So the work is not a vector, right? The work is a scalar unit. Because we know that as we multiply two vectors through a dot product, we get a scalar. What is the work that I'm getting paid for? Well, it's the amount that I am using the force to press this pen against the screen, and it leaves the distance behind. See that? Then I paid whatever cents per mile I draw, and there you go, right? That's the type of work. Now someone else will be pushing the crates, right? And it's also force times the distance. So now you have the Mother Earth and you have the crate. And now you push that crate with the force F. Now if we ignore friction and all the other cool things that you can add to this, you know that this crate is going to move. Now you can't ignore friction and other things. I'll explain why, but if you think about this, so you have the vector, the force, right, F, and if there's no friction here or anything, right, you will move the crate from here to here, which is the distance. Now that distance is measured by the vector D, and the new location for the crate will you can calculate the amount of work, and then you can charge for that. Now, the way it actually works is you have a normal force, which is the weight of the crate, because the crate, right, the crate that it's lighter is easier to move, and the heavier one, it's harder to move. So what happens is that you have a friction, and there's a coefficient of friction. There is a static and kinetic and so on. Doesn't matter the details. Now, that friction is going to oppose the push. So if you push from this side, the friction will go back. Now, friction little force F is going to be the coefficient of friction mu times the normal force. The normal force is perpendicular to the surface, right? And then you also have the weight that it's pushing straight down. Now, this is again still not on the incline or anything like that, so these forces all equal out. But if you observe this case, you see there's the weight of the crate, and the normal force is actually negative W, right? Because in this case, there's nothing else. And the friction is, this is just too convoluted here, so we have the W, which is the weight. That's mass times the gravity. And this puppy here is the friction force, which is mu n. Now you have if the block is stationary, you have the coefficient of friction S, which is stationary, right? Static, and then you have kinetic one when it starts moving. So so you can see that the heavier the crate, the normal force is a larger number. The larger number goes in here and makes the friction force larger, which means this force needs to be larger to counter all of that, right? So you have to beat the friction. It's much easier to move the fridge on ice than on asphalt, right? If you're dragging it. Coefficient of friction is much lower on the ice, right? Now, the game of negative signs over here also, remember in physics everything is which way it goes. So yeah, that's a negative W, but then also force and the friction force have opposite, right? So minus and minus cancel, and then it all works out in terms of, yeah, this is the amount of force that counters the other amount of force. So when you are talking about this situation here, you can clearly, right, see. Now, really there's not much for us to do here. As long as you know how heavy the damn thing is, you can just follow all the steps back and see what you need to push. But people don't push properly, right? What people do is they lean, right, like this, and push. Now, what's the issue here, right? Look at my angle. You see this? This angle that I have here, right, has the component that it's trying to bury what I'm pushing into the ground, and that's not happening. So that's the wasted part. So how much is actually the component that I'm using? It's the projection one, right? So if you carefully decompose the picture that I had earlier, so if you are pushing at an angle, and just observe yourselves or anyone else that it's pushing, right? You push something at an angle like this, well, shine the light from this one, and it's going to produce that red vector. Now, that's actually just decomposing vectors with sines and cosines, sure. But if you really want to see projection at work, there you go. The only one that does the work here, right, is going to be the projection of a force vector onto the surface on which you're walking on. I can put this on the incline, it's fine, right? So now you're thinking about these concepts, and you see that's the projection portion, and then whatever else is there, which you can also find through decomposing the vertical component, is the one that gets buried because you can't bury this. Now, you go on a sand and try to do this, yeah, you're going to start burying this thing into the sand. Right? Because, you know, all of those things of how the pyramids were built just makes so much sense, right? Because it's so easy to move a half-a-ton block or a 2-ton block on a sand surface. It's not a problem, right? You just need to push harder and have more slaves. I'm talking about 2.2 million blocks that are perfectly stacked. I know. With a quarry that was in Washington, D.C. That's 300 miles away. So all you need to do is to just, you know, cut out the block. That's easy, because you have bronze tools for that. And then just put it on a boat. It's not a problem. Send it down the river, right? We do that all the time. Just unload that without a pulley or a crane, because it still didn't exist. And then just, you know, a few miles to the site. And then stack it up. Not an issue, as you can see. Multiple ones. The ones in Mexico the same way and everywhere. Nice. So, the first time that no one screamed aliens.
I was thinking that. It's like just build it on the alien planet, just teleport on, and they just...
Exactly. Build it on an alien planet, just teleport it here. Exactly. So yeah, there you go. What happened?
When you said that, I was like...
Careful.
Okay, so this vector would be... So, guys, so the red arrow would be again the projection of the force. So I'm just going to point like this, and I say this is the component of the force which does work, right? In the sense that work is force times the distance that you have to cover, right? So that's the component, and that force is the projection that we covered, projection of the black force. So I have a black and a red force now, right? The black force is the force that you are pushing with, but the red force over here is the force that actually does the work, and the blue force is the one that it's wasted. So there are the three color forces there. So it's a projection onto the projection onto the floor, right? Could be inclined or whatever it is, right? So that's technically that's it. And when you have a problem, you quickly figure out whether it's just a basic problem, you just push straight. I believe like one on your lab or something like that, or it's on the incline, right? Which you guys are going to encounter as you move through your physics courses and so on. It's plug and chug, right? You have the F, you can calculate the F, and the distance D you have to go. So technically, that's that. I mean, we can. All right, here. So let's take a look at. So they say a force F in third-dimensional space given as 332. No, 332. And you need to move something from point 10110 to point 660. Yeah, well, great. Is this going to create, if this is P and Q, that's going to create a PQ vector, which is your distance. And that vector is 550. right? When you subtract 6 minus 1, 6 minus 1, 0 minus 0. So you have that, and you have the displacement, right, which is the distance it goes. Distance and displacement not the same thing, right? But loosely speaking, yeah, we're not supposed to. So what's the work? You just dot this and you're done. So 1530 joules. Now I have a conceptual question to see if you are mentally here. Looking at the last line, the one that says W and then dot product of two vectors equal 30 joules. Looking at that, are we pushing up? And how far up did the object go?
It's a scalar.
Why are you talking pushing down
What?
pushing down 3 units?
Why down?
That's the z-axis.
Z-axis is on +2, that will be 2 units up. I know. You see, is there any gain in height in a distance you cover? No. This is what I need you to understand. You want to be mechanical engineers, you want to know this stuff, or just want to pass the test and then just be useless later? I'm serious. You want to know it, or you want to pass and be useless, right? I need you to see that the displacement that I went right here. You have the grid up there, right? 5 across and 5 across. So I go, unfortunately these are rectangular. I wish they were all square 2 by 2 things. So you kind of in your mind's eye, you have to divide these midway, right? So you go 5 this way, you go 5 that way. If I go 5, 5, 0, I'm going 5 in x, 5 in y, which means at the same time going 5 in x and 5 in y, I'm going diagonal, which is 5 root 2. The displacement over there in a linear line is 5 root 2. And there is no going up or down because the displacement goes up and down. I was pushing up, but I didn't get anywhere up, right? Because this was zero displacement for me to get anywhere up. So when I lean this way, right? When I lean this way, I am pushing down to it. If this is to move, here, I am pushing forward and down at the same time. Is it going down at all? It's not, right? So you have to divorce those two things. You have the force, which goes 3 in x direction, 3 in y direction. That's 3, 3, right? And down. How do I, well, and up, 2 up in this case. So which way am I pushing? So I need to push 3 in this way, 3 this way, and 2 up. So I'm actually pushing, this is 90 degrees, 90 degrees, I'm pushing at 45. So I'm pushing 3 root 2 in the xy plane, and then together 2 up. But the displacement that I'm getting, for whatever reason, maybe I hit the ceiling, I can't go up anymore. I'm not getting anything up, it's just 5 and 5, so it goes just forward. And it doesn't gain any height in that, right? And we're getting the scalar unit here, that's just how much work was put into it. So these things are telling us what's happening in terms of, right, how much work you used. You can calculate other things other than that, like the power and all that other stuff, but we don't care. And yeah. Now you have 3 pages of problems. Let's take a break. Cross product when you come back. If you're coming back.